So in today's class, we'll be discussing about electrochemistry and the related facts about it to solve the multiple choice questions. So here if we consider what do you mean by electrochemistry, the word itself indicates electro stands for electrical energy, chemistry stands for chemical energy, and here we will be discussing the interconversions of electrical and chemical energy. In this we'll be basically studying about electrochemical cells. So electrochemical cell means conversion of electrical energy to chemical energy or conversion of chemical energy to electrical energy. The device which is used to do so, we call them as electrochemical cells. In that there are two types of cells. One is galvanic cell, another is electrolytic cell. So in galvanic cell, we see that it converts chemical energy into electrical energy spontaneously. Spontaneously means in first PU you have studied about it, the reaction takes place on its own. And for such a reaction, we represent the Gibbs free energy change delta G as a negative value, which indicates that the reaction is occurring on its own. Next is electrolytic cell. Electrolytic cell converts electrical energy into chemical energy non-spontaneously, and non-spontaneously means the reaction does not occur on its own. It takes help or it needs some aid for the reaction to be carried out, and its Gibbs free energy change we represent it as delta G equal to positive. In galvanic cell and in electrolytic cell, we see that anode is negatively charged, cathode is positively charged. Electrolytic cell, anode is positively charged, cathode is negatively charged. Irrespective of their charges, always at anode, oxidation reaction will occur, and at cathode, reduction reaction occur. And the most common example for galvanic cell or voltaic cell which we can consider is Daniell cell. So it's a galvanic cell. Galvanic cell means which converts chemical energy into electrical energy, containing zinc rod as anode. So this you have to remember, a electrochemical cell where zinc rod is anode and copper rod is cathode, we call it as a Daniell cell. So overall chemical reaction is represented as zinc plus copper ion forming zinc ion plus copper. Its cell representation is done in this manner. So zinc in solid state, zinc ion in aqueous state. That means this is oxidation reaction which occurs at anode. This is the reduction reaction which occurs at cathode. And anode and cathode are connected. These are two half cells. These are connected to each other by a salt bridge. So for any electrochemical cell, you can represent it in this manner by writing anodic reaction first and then a double line, then cathodic reaction. This double line indicates nothing but salt bridge. Here anodic reaction, atom or a molecule or an atom converted to its ion by an interface, separated by an interface, is anodic reaction, and ion getting reduced, separated by an interface, is cathodic reaction, and this overall we call it as cell representation. And the potential difference between the two electrodes can be calculated by calculated as electrode potential is given as E naught cell equal to E naught of cathode minus E naught of anode. So if you consider here, E naught cell equal to E naught of cathode, cathode was copper, anode was zinc. Their values are there in electrochemical series, and overall the cell potential produced by Daniell cell is 1.1 volt. To calculate that cell potential of different electrodes, we use a reference electrode which is called as standard hydrogen electrode SHE or normal hydrogen electrode NHE. The cell potential of this is assumed to be 0.0 volt. Cell reaction, we can represent it as H plus electron forming half H2, and it's a cell representation platinum. H2, it is in gaseous state at a pressure of 1 bar, and bar H plus ion aqueous 1 molar. So after that, Nernst equation to calculate the cell potential at any concentration and at any temperature T. So to calculate the EMF of a cell at any concentration other than 1 molar, we can make use of this equation at any temperature T. And it is given as E cell equal to E naught cell minus RT by NF into ln of anode ion concentration raised to the power X, where X is the number of moles of anode ion in a balanced equation, and Y is the number of moles of cathode ion in a balanced equation. Or it is also given as E cell equal to E naught cell minus 2.303 RT divided by NF log of anode ion to the power X divided by cathode ion to the power Y. The same equation, if at all the temperature is 298 Kelvin, we can calculate it as E cell equal to E naught cell. In the above equation, if you substitute the value of R as 8.314 joule per Kelvin per mole, T as 298 Kelvin, and F value as 96,500 Kelvin, you get the near about value as 0.059 volt, and divided by N, log of anode ion to the power X divided by cathode ion to the power Y. So N value here or here or here, we can't write it directly. It depends on the reaction which is occurring. So here the value of N is number of electrons gained or lost, as they should be equal. So that should be equal. Number of electrons gained should be equal to the number of electrons lost. Hence, we'll try to write the same Nernst equation for Daniell cell. So in Daniell cell, we had seen zinc was acting as anode and copper was acting as cathode, and based on it, this is the equation. So here anode ion is zinc ion, cathode ion is copper ion. N value, number of electrons lost and gained, are equal to 2. EMF of a cell is equal to 1.11 volt. In the previous paper, we have seen about the E naught calculation for Daniell cell. So if you write this equation, Nernst equation here, E cell as it is, E naught cell 1.1 volt, 0.059 volt divided by 2 log of anode ion is zinc ion 1 mole, so anything raised to 1 remains as it is, divided by copper ion, it is also 1 mole, so it will also remain as it is, and this becomes the Nernst equation for Daniell cell at the temperature 298 Kelvin and at any concentration of zinc and copper. Next is electrochemical series. So electrochemical series is defined as the arrangement of electrodes with the electrode half reactions in order of the decreasing standard reduction potential. So if we compare it to the NCERT, there is a electrochemical series given where the electrode potentials are measured at 298 Kelvin and arranged in the decreasing order. So which is given in NCERT, will represent it. So if you look at your NCERT textbook, even in first PU in the lesson redox reaction as well as in second PU, they have given this electrochemical series are arranged in the decreasing order. Here you can see that fluorine easily undergoes reduction and hence it is having a positive electrode potential value. As we move down here, the tendency to undergo reduction decreases. That means its oxidizing power is decreasing, but its reducing power is increasing. And at the last, if we see, lithium ion undergoes reduction to form lithium and it has a negative potential. Thus, based on this electrochemical series, we can say that if it is based on the electrochemical series, if we consider lithium ion is not easily undergoing reduction because it is having a negative value. Instead, the reverse is easy. It will undergo easily oxidation. Whereas, if we consider the first reaction, fluorine was easily undergoing reduction and forming fluoride ion. That means it was undergoing easy reduction, so it has got a positive value. Whereas the reverse of it is very difficult. It's difficult to remove the electron from the fluoride ion because fluoride being more electronegative. Thus, we can say that fluorine gas is the strongest oxidizing agent as it is easily undergoing reduction, whereas the fluoride ion, fluorine gas is the strongest oxidizing agent, but fluoride ion is the weakest reducing agent. And similarly, since lithium has the lowest electrode potential, lithium ion is the weakest oxidizing agent, but lithium metal is the strongest reducing agent based on the electrochemical series. So we'll try to understand what are the applications of this electrochemical series. Electrochemical series are used to calculate the EMF of an electrochemical cell to predict the relative strength of oxidizing and reducing agent as we have discussed now. So we can say that based on the E0 cell value, we can identify whether the given compound or the given ion or molecule is a better oxidizing agent or reducing agent. And we can also predict the feasibility. Feasibility refers to spontaneity of the reaction. We can also predict whether the metal will react with acid to give H2 gas, or a metal will displace another metal from its salt solution or not. So how can we predict it? That also we'll try to understand by referring to the electrochemical series. So here, how to understand whether one metal is more reactive than the other or no, we'll try to understand. As we have said, hydrogen is taken as a standard. The metals which are present above hydrogen cannot displace hydrogen in the form of hydrogen gas. That means the metals present above it are less reactive, whereas the metals present below it can displace hydrogen ion in the form of hydrogen gas, hence they are more reactive. So if you take a couple of copper ion and zinc ion, that is Cu2 plus and Zn2 plus, so redox couple if we want to prepare from this. So one we have taken copper, another we have taken zinc. For copper, the E0 value is plus of 0.34 volt. For zinc, the E0 value is minus of 0.76 volt. So we have discussed that as the E0 value decreases, the tendency to undergo oxidation increases. Hence, zinc can easily undergo oxidation, whereas copper ion can easily undergo reduction. The one which is undergoing oxidation can act as anode, the one which is easily undergoing reduction can act as cathode, and hence we can use this to frame a redox couple. So these are the applications of electrochemical series. Next if we consider equilibrium constant from Nernst equation. So if we say any reaction is at equilibrium, so if at all we consider the reaction of the kind A plus B is at equilibrium with C plus D. Now under this condition, how can we find out the equilibrium constant Kc? By comparing it with the E0 cell. So for this we use the Nernst equation. If any reaction is at equilibrium, the cell potential also becomes equal to 0. Thus, using this Nernst equation at any temperature T, the E0 cell becomes equal to 2.303 RT by NF log C. If we substitute all the values in temperature T, so if you are taking T as 298 Kelvin, R equal to 8.314 joule per Kelvin per mole, and F equal to 96,500 coulomb, the above equation can be written as 0.059 volt divided by N into log Kc. Or you can calculate it by taking in this manner. Kc you keep it as it is, E0 cell into N divided by 0.059 volt, anti-log of it will give you the value of Kc. So this is how we can calculate the equilibrium constant Kc if we know the EMF of a cell at 298 Kelvin. Another most important topic, that is Gibbs free energy. So Gibbs free energy is given by the equation NFE cell or delta RG naught equal to minus NFE naught cell. So delta RG is change in Gibbs free energy, delta RG naught is change in Gibbs free energy under standard condition. We can even calculate change in Gibbs free energy by the equation minus RT ln K. Now we can relate delta G, E naught cell and K by the relation. So we'll consider that we are having E naught cell value. We'll find out the delta R G naught value as well as K value based on it. So we have E naught cell here. If E naught cell is positive, overall E cell or E naught cell, if they are positive, plus into minus is minus, you get delta G as negative. That is delta G, you get it less than 0 or less than 1, or you can say it is negative less than 0, sorry. If delta G is less than 0, then K, equilibrium constant, you get it as greater than 1. This is a relation you have studied already in first PU. Similarly, if your E naught cell is negative, delta RG, so E naught cell negative, negative, minus into minus becomes plus. If minus into minus is plus, delta RG naught becomes positive. If delta RG naught is positive, it means delta G is greater than 0, and if delta G is greater than 0, K will be less than 1 as we are relating it to the negative logarithm of K. Thus, based on this, we can derive the relation between E naught cell, delta G as well as K. If your E naught cell is 0, delta G also is equal to 0, and in this case, K becomes equal to 1. Next, if we consider resistance, resistivity, conductance, conductivity. Resistance is directly proportional to the length and the area unit square. And here we take a constant rho, which is called as resistivity or specific resistance, and rho can be calculated as R into A by L, where R is the resistance in ohm. Area is area in terms of meter square or centimeter square based on the units given, length in meter or centimeter. Similarly, conductance is the reciprocal of resistance, so G is equal to 1 by R. G is equal to, by substituting the value of R here, you get the equation A into rho by L. 1 by rho can be written as kappa, which we call it as conductivity or specific conductance. Hence, substituting it, we get it as G equal to K into A by L. Now here L by A is a cell constant, which is represented as G star. So G star can be written as L by A, or it can be also written as G star is equal to R into kappa, that is resistance into conductivity. Next is equivalent conductance. Equivalent conductance depends on normality of a solution. It is given as equivalent conductance equal to kappa into 1000 divided by normality. Molar conductance in terms of Siemens per meter square per mole, it is given as lambda m equal to kappa divided by C into 1000, where C is in concentration mole per meter cube. Here lambda m is equal to kappa into 1000 divided by C mole per liter, and just to convert it into terms, we have divided it by 1000. So this were the formulas which you should remember while solving the problems on multiple choice questions. Next is variation of conductivity, molar conductivity and equivalent conductivity with dilution. So if we consider here conductivity kappa, it decreases on dilution, whereas molar conductivity and equivalent conductivity increases with dilution. We can relate them by the equation lambda equal to kappa into V. So if you consider here, lambda is directly proportional to volume V. Whenever you dilute any solution, its volume increases. So it's whether it is molar conductivity or equivalent conductivity, both will increase on increasing in the volume, that means with the increase in dilution. But if we rearrange this equation, we get it as kappa is equal to lambda divided by V. So based on this, we can say that conductivity kappa is inversely proportional to volume. Inversely means on dilution, if the volume is increasing, the conductivity is decreasing. And why it happens here, why conductivity increases here and conductivity decreases here, Here we see that with the increase in volume, the area carrying 1 mole of electrolyte or 1 gram equivalent of the electrolyte increases. Hence, the conductivities are increasing. That is, molar and equivalent conductivities are increasing. But here if you consider the area carrying the number of ions per unit area, they decrease on dilution and hence conductivity also decreases. And on dilution, when the concentration approaches 0, the molar conductivity is known as limiting molar conductivity, represented as lambda m naught. So for strong electrolytes, the molar conductivity increases slowly with dilution and can be represented by an equation called as d by Huckel-Onsager equation. It is given as lambda m equal to lambda m naught minus of a into root c or c to the power 1 by 2. Where lambda m is the molar conductivity, lambda m naught is the limiting molar conductivity, a is a constant and c is nothing but concentration of the solution. To determine the limiting molar conductivity of either a strong electrolyte or weak electrolyte, we study a law which is called as Colrausch law of independent migration of ion. Limiting molar conductivity of any electrolyte is given as the sum of the individual molar conductivities of cation and anion of electrolyte. So it means that if at all we want to calculate the molar conductivity, limiting molar conductivity of NaCl, we can calculate it as lambda naught of Na plus of lambda naught of Cl minus. Similarly, if we want to calculate the limiting molar conductivity of acetic acid, we can calculate it as lambda naught of CH3COO minus plus lambda naught of H plus. Then next, Faraday's first law. So laws of electrolysis, there are two laws of electrolysis, Faraday's first law and Faraday's second law. The statement of Faraday's first law is the amount of chemical reaction which occurs at any electrode during electrolysis by a current is proportional to the quantity of electricity passed through the electrolyte. So whatever the amount of reaction is occurring, it is either in the form of amount of substance deposited onto the electrode or amount of substance liberated from the electrode, and it is directly proportional. So W is directly proportional to the current passed in amperes and the time in seconds, so which is given as IT. So to remove this proportionality sign, we take W is equal to ZIT, where this Z is calculated as E divided by 96,500. E is nothing but equivalent mass, and equivalent mass we can calculate it by atomic mass divided by the number of electrons required to reduce the cation, and based on this we get the E value. If you substitute the E value here, I value here and T, we can find out the mass of the substance deposited or displaced from an electrode. Similarly, if we consider Faraday's second law, so Faraday's second law states that the amount of different substances liberated by the same quantity of electricity passing through the electrolytic solutions are proportional to their chemical equivalent weights. So when you are passing same quantity of electricity through the electrolytic solution, then the amount of different substances, so here if we take two different substances, they will be directly proportional to their equivalent weight. So W1 by W2 equal to E1 by E2. So this was Faraday's second law of electrolysis. Then the last topic here, batteries. In batteries we have primary cells, secondary cells and fuel cells. Primary cells which cannot be recharged further, we call them as primary cells. Secondary cells which can be recharged repeatedly, so it can be recharged repeatedly on discharging, we call them as secondary cells. And fuel cells, here the combustion energy, the energy of combustion of fuels is converted, so it is a type of chemical energy, that is combustion energy, it is converted into electrical energy. And one of the example for that is H2O2 fuel cell. For secondary cell, in your theory portions you have studied about the lead storage battery, you can remember the examples of that. And in case of primary cells, you have studied about Leclanche cell, you can consider that, or mercury cell to remember the examples. And next is corrosion. So corrosion, it is nothing but what comes to mind on hearing the word corrosion is rusting of iron. So rusting of iron occurs as an redox phenomenon. We see both oxidation and reduction reaction here. So what is the oxidation reaction that occurs here? Fe in solid state, due to the atmospheric conditions, undergo the change and undergoes oxidation to form Fe2 plus ion with the loss of electron. The reduction reaction that is occurring is O2 in gaseous state results in the formation, plus of 4H plus of 4 electrons result in the formation of 2H2O. Further, when we add these two reactions, just to balance the number of electrons lost and gained, we'll multiply this equation by 2. What do we get here? Then final equation 2Fe in solid state plus of O2 forming plus of O2 plus of 4H plus forming 2Fe2 plus of 2H2O. Now this undergoes further atmospheric oxidation. Now when it undergoes further atmospheric oxidation, we get the product as iron rust, which we can represent it as 2Fe2 plus of 2H2O. We are saying it is undergoing further oxidation, so half O2 forming Fe2O3 in solid state plus of 4H plus in aqueous state. So overall, what we get it as a rust in hydrated form, we call it as, or whatever we are getting this as rust here, we call it as iron rust or rusting of iron. And here this is occurring due to the oxidation of the products of anodic and cathodic reaction. So you may get a question on this. Rusting of iron, if they give the question as is an reduction reaction or oxidation reaction or hydrolysis reaction or precipitation reaction. So we know that rusting of iron includes both oxidation and reduction, but here they have given specifically only reduction, only oxidation, hydrolysis or precipitation. So the correct answer is oxidation, because rust is obtained by oxidation of the ion. But if they generally ask, if instead of this, if there is an option known as redox, then you have to consider redox to be the better answer over oxidation, because only iron rust is obtained by oxidation. But overall, to get that iron rust, we see both oxidation and reduction process. So using this, we will be using this concepts, we will try to solve some of the multiple choice questions in the next video. Thank you for watching.